Okay, let's start. So I'm very glad to introduce Cristian Mariani, who you already know, surely, who's going to talk about non-Markovian collapse models.
Great, thank you. So the reason why I'm doing this is mainly because in the last talks of this Lugano Philosophy Colloquia, there were supposed to be talks in philosophy of physics, but in one way or another, they were either on logic or on metaphysics. So I thought I should do some physics for, I don't know, very few people. I think there's 5 or 6 people who are actually interested in what I'm gonna say. No, well, maybe tomorrow there's gonna be 7. That's my hope. So yeah, I've been interested in collapse models, which is an interpretation, family of interpretations of quantum mechanics for quite some time now. And I kind of read a few papers on these non-Markovian models while I think 2 or 3 years ago, before some philosophers, which I'm going to mention, Builes and Impagnatiello, I hope I pronounced him correctly, wrote a paper on the consequences of non-Markovianity, and the title of the paper is An Empirical Argument for Presentism. Hello. So, well, I kind of went back to these papers from Adler, Stephen Adler, and Angelo Bassi, with a different kind of interest, to see whether there were any kind of interesting philosophical stuff to gather from those papers. So Tim is teaching quantum mechanics this year, which is very good. I don't know how far you got, whether you did interpretations. So I'm gonna introduce some of the stuff for those of you who don't know them. I think it's gonna be hard to follow anyway, but I'll try to kind of say something. Ciao. Milo is gonna help me. So yeah, I wanted to start with this quote, which I admit I didn't read the book, which from where it comes from. It's written for a nun from Faulkner. I actually knew this quote because of Obama. In 2008, he mentioned this for a completely different reason from the reasons why I'm mentioning this quote. Obama refers to the fact that in the US, right-wing movement and the Tea Party were still back in 2008, alive, very much alive. And that's why he gave this quote. And he happened to be right. Now we know that for sure. I mentioned this quote because, non-Markovianity, Markovianity and non-Markovianity has been obviously related to whether or not the past is still influencing, in some way of influencing, which I'm going to say something about, the present and the future. So on Markovian, the standard understanding, Markovian processes or Markovian dynamics are those where, in order to predict the future state, we only need information about the present state. Whatever happened in the past, whatever led us to the present, to that specific present state, is irrelevant. In the non-Markovian case, the negation holds. So in order to predict future state, we need information about the history of the system, at least part of the history. And that's why I thought this quote was useful. So let me give you an overview of the whole talk. So we all know that quantum mechanics is incredibly successful to predict, to make predictions, at least what Tim calls the recipe. It's very helpful for us to make predictions about the future state. So it's a successful theory. If there's any such a thing as a successful theory, then definitely quantum mechanics is one of those. And it is, in fact, so successful that it would be, here I'm using kind of a realistic argument, it would be incredibly miraculous that the theory is not telling us something true about the world. How should we explain the success if not because the theory is somehow true? But then if we, that stuff, if you start asking what exactly the theory is telling us through, people kind of disagree about literally everything. There are indeterministic interpretations, deterministic ones. So at least on this topic, there is no final verdict in quantum mechanics. Bohmian mechanics is deterministic. Spontaneous collapse, which I'm going to speak about, are not. There is a huge debate on the interpretation of Bell inequalities, what kind of interactions are non-local interactions, even how to call them, there is a debate. There is obviously a debate about the ontology. There is obviously a debate about the interpretations, you know that, the measurement problem. So everything, almost everything is controversial. And on top of all these issues, which probably you heard about at least once in your life, there is a slightly more neglected one, which relates to what we may call, here I follow Adlam and a bunch of other people, temporal non-locality, or lack thereof. So this is, I would say, slightly more neglected. There is some people who discuss that, but definitely not even remotely as the other topics have been discussed. And as I already anticipated, this is connected to whether or not the underlying dynamics is Markovian. So most approaches to quantum mechanics, virtually all of them, apart from the ones I'm going to speak about today, assume that the underlying dynamics is Markovian. So as I said, this means that in order to predict future state, we only need information about the present state. The past doesn't matter. The past is dead, in the sense that there is no influence from the past to the present or to the future. In any way, in any sense of influence you may have in mind, that is dynamically relevant. And of course, there is a lot about, to say about what motivates Markovianity, what's behind Markovianity. In a way, it's a kind of a, how to say that, hardwired in the very way in which we look at the world. It makes things easier to treat mathematically. And so it's kind of safe and normal to assume Markovianity, to want our theories to be Markovian. However, in at least in what is definitely one of the major approaches to the solutions of the measurement problem, which is the spontaneous collapse model, at least in that context, the jury is still out with respect to whether the word is Markovian or not. So briefly, again, I hope you heard something about those views already. So the key feature of those models is that the wave function undergoes a continuous, a random, spontaneous, not continuous necessarily, a random and spontaneous process of localization, which explains away the problem of the measurement problem. We only get one dynamic, both for microscopic and macroscopic systems, the same dynamics. I'm going to say a little bit more. And the standard versions, so those approaches to quantum mechanics are inherently fundamentally indeterministic, stochastic. And in order to achieve the stochasticity in these models, what people do is to kind of add what Stephen Adler and Angelo Bassi call an imaginary noise trick to the fundamental equation in order to achieve the stochasticity. And in all the standard models, in all the standard spontaneous collapse models, such noise term is white in time. I'm going to say a little bit more about what this means. But that's related to Markovianity, spoiler alert. I mean, for some of you, this is obvious, some of you, it's not. So there's been recently, well, not so recently, in the last 15 years, for me it's recently, but maybe it's not, generalized versions of those models with non-white noise have been explored by Adler, Bassi, Girardi wrote something on this. So I believe that if we look at Markovianity and at the consequences or lack of Markovianity, on the consequences of Markovianity, the cost of the rejection of this property, in the context of quantum mechanics, this is an ideal place to look at. And this is why I'm going to focus on this today. So of course, like from a broadly naturalistic perspective, this has a lot of impact on many views, on possibly on ontology, temporal ontology. I am skeptical about the temporal ontology part, and I'll tell you why. Less skeptical about causality and counterfactual. But in general, this is, at least according to, this is my opinion, these models are a very good place to look at because they are good solutions to the measurement problem. There is non-Markovian models which are not what I'm gonna call realistic interpretations or realistic approaches to quantum mechanics. So within the camp of the people who take seriously the measurement problem, this is definitely the ideal place to look at if you wonder what are the consequences of Markovianity. Because again, these people have seriously considered having no Markovian models. So that was the introduction. What I'm gonna do is first introduce the spontaneous collapse model. Again, for those of you who don't know them, this is not gonna be very useful. For those of you who do, it's gonna be useless. So, but I have to kind of do something. Okay. So this is a little bit more interesting. I'm gonna give you the general, well, one version of the generalized continuous spontaneous localization equation with the non-white noise. And I'm gonna kind of compare the two very quickly with respect to Markovianity. And then I'm gonna discuss the philosophical consequences, which I mean, in my head, that was the fun part. I still think it's fun to some extent. But I think I'm not gonna say too much apart from kind of complaining about Builes Impagnatiello. Nothing much. There is something I care about, and which is also the reason why I started getting interested in all of this, which has to do with the role of the wave function in the continuous spontaneous localization model. You know, that there is a debate about how to interpret the wave function in quantum mechanics. In every approach to quantum mechanics has its own problems about the wave function, and there are also general problems which everybody has. But in the case of continuous spontaneous collapse models, there is a way to kind of look at the wave function as simply coupling two physical fields if we look at the noise field in a kind of new way. So this is going to be the new thing of what I'm going to say today. So two consequences, one on temporal ontology, I'm going to complain about people who argued about this connection, and two, reality of the noise field, what I say, what I call noise field realism. Okay, let's start. So these are, as I mentioned, one of the major approaches to the measurement problem. Tim was here as this very useful way to introduce the measurement problem in his paper from 1995, where he presents the problem as a trilemma, where you cannot keep three things that we all wish to keep: linearity of the wave function. Now I forget them. Unicity of outcomes, and wait, not that. Wait, let me get linearity, unicity of outcome, and that completeness, of course, because yeah, that's the one you want to reject. I like rejections of linearity. This is a rejection of linearity. Rejections of completeness are Bohmian and other approaches, and rejection of unicity of outcome. You call it unicity, right? Uniqueness of, okay. Uniqueness of outcome, such as Everettian quantum mechanics. So this is useful because you cannot have all of these three: linearity, completeness, unity of outcomes. You have to reject this one, and depending on what you reject, you're gonna lean towards one of the major realist interpretations. There's other interpretation, of course. Orthodox interpretation in a way rejects linearity, but in a way, in a way that many find, myself included, unsatisfactory. There's Rovelli's interpretation, and there's a debate about which of those three would reject. I'm not certain. Anyway, so these models reject linearity. So basically what they do, they propose a modification of Schrödinger's equation. They add a stochastic and nonlinear term, which allows to explain collapse of the wave function, not as something that we do when we measure, or we do when observers interact with microscopic systems, as in a sense, in some sense, is the case. Well, at least the word measurement is kind of primitive in standard approach. In this approach, it's explained, collapse is explained. It's not a primitive, it's not something we don't know when it happens, but it happens following the fundamental equation of those models. So there's two main approaches to how to fix, well, how to modify the Schrödinger equation, adding nonlinear stochastic term. One, the first one in history was proposed by Girardi, Timing, and Weber in 1986. Well, Schrödinger's equation is supplemented with another term which explains the collapse. And the collapse is described as discrete events, one after the other. Then there is the continuous spontaneous localization model, first proposed by Pearl, CSL. And today I'm going to mostly speak about CSL for a number of reasons. So almost everyone, Girardi and Bassi included, in late years have been focusing on CSL mostly for a number of reasons. In this case, the case that matters to us today, the reason is that the non-Markovian generalizations are made in that context. Girardi made a few remarks in 2016 about GRW, non-Markovian, so this one. But it's going to make things easier to look at CSL. Well, there is a number of differences which are interesting, but not today, so I'm going to just skip those. Well, it has a wider range of applicability, this everyone agrees, so at least for this reason, we should keep in mind that CSL is, to some extent, better. Okay, so this is the equation, which again, if you know Schrödinger's equation, the first term is the Hamiltonian. So this second term is quite crucial to understand this equation, these models in general. The third term contributes to the collapse, but and also preserves the normalization of the state. But what's important is this one. So again, that's the standard Hamiltonian. Here we have two terms. One is the mass density operator, mx, and one is the noise, wtx. So if you look at this, there is already kind of an interaction between those two fields. Now, philosophers have been discussing, and I definitely agree, of the possibility that looking at this equation, we should interpret the continuous spontaneous localization models as referring to an ontology that consists in the mass density distribution. And of course, depending on the state, the mass density could be the mass density of the whole universe. This in turn is defined in terms of the number of particles of a given type in a certain region. Now, I thought that this is crucial because first, it introduces the collapse mechanism by introducing the field, the noise field, and second, it introduces kind of the ontology, if you care about ontology. There it is. And maybe here I'm going ahead, but of course, already at this stage, there is a sense in which WT is on the same, as the same importance, physically relevance of M, if you look at the equation. But Bassi and Girardi, other, are quite explicit that this is, they call it a noise trick, a trick, just to introduce stochasticity. We'll come back to this. When they want to kind of describe what the ontology is, philosophers look at M. So the ontology, according to this interpretation of these models, is a continuous distribution of mass spread all over the universe. Okay, gamma contains the collapse rate parameter. And well, that's not really relevant. Gamma is relevant, I'll come back to this. So gamma is the rate at which the system undergoes a process of localization at some point in space. Okay? So in the standard version of GRW, this is quite high, it's 10 to the minus 16, which means that if you take a single particle alone in the universe, it would on average collapse once every 100 million years. So not very much. But the trick is very useful because if you put a lot of them together, one of them will collapse, and by being entangled, by being related, connected to the others, they're gonna produce the collapse of the whole system. And this also explains why, if we look at the double slit experiment, there is no collapse, so we see interference effect. If we take the screen at the end, there is enough particles that are going to produce a collapse. I'll come back to this. I said 10 to the minus 16. Keep this in mind just as a number. Okay. Now, I said white noise. What does it mean? We can define a white noise using these two very formal properties. So zero mean, it means that the noise at any point is unrelated to the noise at any other point. So if you take any point in time, the value at previous points is completely irrelevant for you to know the value at this point. Delta correlation, again, it doesn't really matter, but the point is that we can gather three properties out of the description of a white noise. Here, I don't mention the distribution because I wanted to keep things simple. And also, I'm talking about a time-only case. In the case of CSL, we introduced space as well. I just wanted to keep things simple. So in the case of a white noise, the point is that, again, it's a mathematical idealization, and it's not measurable at any point. So in a kind of a strict sense, it's not really a function because it's not measurable at any point. I call the second property equality because this is why it's called white, because it has equal power at all frequencies. So the systems will be excited in the same way, independently of the frequency. And third, the memorylessness, which is the hallmark of the Markovianity. There is no memory of previous interactions or states. So the value at any point in time is independent of the value at any other time. So if we look, so this is in general, again, independent from CSL.
Is it time dependent?
So this is only time, space. So again, this is super idealized state. Now I'm going to introduce the CSL where you have space and time.
Because in the previous one, just a spatial integration, right?
Yes.
So there is no time dependent.
Well, this is time dependent.
Ah, yeah, okay, of course. Okay. I was thinking about the noise. Just because it's here. Ah, okay. Well, sorry.
Okay. CSL. So that was general, any white noise. So the white noise in CSL, we have to consider both T and X. And we're going to have a different delta function, direct delta function. So the noise is, again, uncorrelated in both in space and time. This is what we're saying with this. And again, knowing the value of the noise at any point in space or time is not going to give us information about the field, the noise field, at any other point in space or time. It tells us nothing about elsewhere. So we can think of this as a field that fluctuates very rapidly, in an incredibly rapid way at any point, which is not really physical in a way. Again, it's an idealization. But by fluctuating so rapidly and so vividly, we basically at each point in time we completely lose information about. At any point in time, negative or positive value at the the following time are equally large. That's another way to say it. So there is a sense in which it's local both in space and time. There's also a sense in which it's CSL. I'm just going to mention this, but I hope it's not confusing too much. There's also a sense in which in CSL it's not local in space because the width of the wave function are kind of spread. But it's not because of the noise. So the noise is local both in space and in time. So, and again, if we look at the three properties I introduced earlier, they apply as equally in this case as in the previous case. Okay, this I'm gonna kind of skip because I thought I was going fast, but I'm not. How much time do I have? We have 45?
Yeah, or like an hour.
Okay, good. So how all this connects to Markovianity and lack thereof? Again, a process is Markovian if the future evolution only depends on the current state and not on the past history. We can look at this. So the density matrix here only depends on this interval. So future state T2 only depends on what happens between T and T2. Which again, this is the hallmark of Markovianity. There is no memory of previous states when we have to use and this is the master equation, which again uses the density matrix described as this. So there is no need to know the past. Again, as I said, this simplifies the mathematical treatment because we can use differential equations, which are local in time. And we will see that in the case of the non-Markovian models, we won't have differential equations anymore. We have integral differential equations. That was not really important. I think the important part is this. So again, if we look at CSL and if we look at these equations, there's going to be an interaction between these noise fields and the mass density, and the noise field is white, which means that it has no memory of past state. So to predict future states, we don't need to know what happened in the past. Okay. Okay. Now let me try and introduce the non-white models. So first let me mention that there are motivations for introducing these models, which I'm not gonna discuss. Girardi in 2016 discusses those motivations, which has to do with potential unbounded increase of energy in those models. And in turn with potential conflict with relativity. It discusses those, but then again, the major, I think, if you have just a quick look at the literature, the major reasons for developing these models have to do with the experimental constraints. I mentioned that the collapse rate, the collapse rate in the standard models is 10 to the minus 16 second minus 1. So Adlam in 2003 proposed a much higher collapse rate, 10 to minus 9. And the reason for this is quite pragmatic and physical. The reason is that if we, in the standard models, if we want to describe the formation, the latent image formation in photography, which is something that back in 2003 was still something. Now we don't, well, we just do digital pictures. But back then, if you want to take a picture of something, you would have to go to the photographer and you would have to, do this work. And if you just think of this very simple physical phenomenon of latent image formation, and if you keep the collapse rate parameter as high as 10 to the minus 16, as it is the case in the standard model, you would have that the formation of the image in photography would have to wait for the light to travel from the image and hit your brain, basically. Bastian, Ferialdi, and a bunch of other people did the math. So what Adler proposed was to increase the collapse rate. And of course, I didn't mention this, but this looks problematic because we don't want to, well, we started proposing these models because we didn't want collapse to be, the process of collapse to be related to us doing things, us measuring or us doing things. Okay? We wanted to have collapse as a physical process that is independent from us. But there are some cases where, like this case, where if there is no interaction between microscopic system like our brain and the physical system, which is in this case the photography, we would not get the collapse. So Adler proposes to increase the collapse rate, so it's easier, collapses happen more often, much more often, so that in this case, collapse would not happen in our brain, but it would happen just with interaction between the light and one grain of the chemical substance, whatever it is. So this would obviously fix the problem. Again, admitting that it's a problem, some people think it's not. But if you think it's a problem, then Adler's proposal would fix this problem. Of course, this would have a lot of noticeable effects because we would be, if Adler is correct, we would not see certain interference effects in systems that are made of a smaller number of particles than the one according to GLW. So for GLW, we can see interference effects of even mesoscopic systems, not in this case for Adler. So as a matter of fact, this is so true that Adler's proposal has been falsified. This proposal that I just mentioned has been falsified experimentally, I think in 2018. So it does have an empirical import of this issue. So the point is that if we modify the dynamics and we allow for non-Markovian dynamics in the equations of CFT, we would be able to save Adler's proposal. Adler's proposal would not be falsified if we keep the non-Markovian instead of the Markovian dynamics. So that's the main reasons why people are discussing those models. The other reason, again, this is probably just me, although Girardi mentioned something. In a way, it's weird that we just said that the white noise is kind of a mathematical identification and it's a trick, but we know that actual physical properties are not like that, are not white. So we can still kind of believe that this is just a trick. But if you think that the equation is describing the fundamental dynamics of the world we live in, then I think it's quite natural to ask, what is this field describing? What is this nice field describing? If it's not an idealization. And the case of the non-Markovian dynamics, as I'm going to mention now, it's quite harder to interpret as just a mathematical device. So there seems to be kind of a double standard. So this is I switched the description with the equation because we couldn't read the equation here if it was here. But the equation is the first term of the equation, the first two terms of the equation are the same as the previous equation. What changes is the third term. So here we are adding a spatial and a temporal correlation function with G, X, Y, and H, DS. And we have a functional derivative that explains how the past states of both y, space, and time s respond to the values of the noise previously. So the integral goes from t to 0. So all the history of the system is affected. So we have to consider all the history of the system. And again, it's not a differential equation anymore. It involves integrals and derivatives. And that's important. I just mentioned this. All the history of the system from t0 to t is contribute to the state. Now, in this case, we have non-trivial temporal and spatial correlations. So there is various ways. I don't know exactly. Well, there's various ways in which we can describe FT. Go in a Gaussian distribution, as an exponential distribution. But in all cases, the idea is that the correlation function is as a non-zero extent in both space and time. And again, this is clearly a rejection of the Markovianity. With respect to the white case, you remember I mentioned 3 properties, non-formal properties. The non-formal properties are all rejected. First, physicality, we can interpret this as a physical field, because physical fields usually have some temporal correlation. The spectral properties are completely different. They are not equal. The rate of collapse is going to substantially depend on the kind of noise. So we can have different kinds of noise so long as they're not white. And the memory, of course, for the reason I just mentioned, the future evolution is going to depend on the past history and not just on the current state. So this allows for more flexibilities, both to design new experiments and to put constraints on previous one. As I mentioned, with this model, the Adlam proposal, which I think is, for many reasons quite motivated, will not be falsified. Okay, now how much time? Okay, I'm gonna. So this was supposed to be the non-fun part, and it wasn't. Now the fun part. So there's 2 major consequences of these non-Markovian models. There's many others. If you're interested, for instance, on debates on retrocausality, this is related to Markovianity and non-Markovianity. Emily Adlam has a paper. There is a debate on analogies and disanalogies between temporal non-locality and spatial non-locality. There's people in Grenoble who are working on this, Cyril Branchard, for instance. But the major, from let's say, a philosophical perspective, the 2 major consequences, I believe, have to do with the ontological interpretation of the noise field and with the connection between non-Markovianity, so the broad class of implications of non-Markovianity, and potentially the ontology, the ontological considerations that come with that. So I'll start with one. So as I said, in non-Markovian dynamics, the system evolution depends on the entire history. Some people kind of interpreted that as having something to do with temporal ontology. So yeah, it's there. Yeah. So temporal ontology is debate on temporal ontology has different positions available at eternalism, presentism, growing block view. According to Adlam, if we look at non-Markovianity, if we take non-Markovianity seriously, we would have to reject presentism. And the reason is that if the past does not exist anymore, how can it influence in the dynamics the present, what happens in the present? So on a kind of similar vein, Builes and Impagnatiello argue for a different argument that also connects ontology and Markovianity. for them, the argument goes from Markovianity to the rejection of eternalism. So the argument they have is that first premise is that our world is Markovian. So the first premise is that apart from some interpretation of classical mechanics where velocity is extrinsic, which are non-Markovian, they say that in all interpretations of quantum mechanics, Markovianity is assumed. So that premise should already be rejected, if not only for the reason that there is non-Markovian collapse models. But the second premise is as problematic as the first one. That is that, according to them, eternalism cannot give an explanation of Markovianity. So according to them, presentism can give an explanation of why our world is Markovian, eternalists cannot. So my whole understanding of the argument is that everything depends on whether we assume, so what we think about the laws of nature, what the laws of nature are, and this also connects to Emily Adam's argument. So all of this depends on whether or not you have a broadly Jungian approach to laws or an anti-Jungian perspective. So my understanding is that if you are Jungian and you are presentist, you have no reason to be worried about non-Markovianity. Because if you're Jungian, in the end, you just think that our laws are the best way to systematize particular effects. So if it happens that the best way to systematize those facts is one where something in the past is influencing the present state, as it is the case in non-Markovianity, presentists have a lot, I think they have resources to deal with that. So I am not a presentist at all, but if you read recent views, recent debates on presentism, for instance, David Ingram, presentism, where they have kind of cases from the past which are still around. I think this will provide resources for the Jungian to be non-Markovian and presentist. I think it's harder for the anti-Jungian presentist, depending on what kind of anti-Jungian you are. I think I'm also curious to hear what you think about this, but my kind of feeling is that if you're anti-Jungian and you believe that in some way laws are actively contributing to produce future states, then if those laws are such that in order to produce future states, they have to, in a way, so the state has to be influenced by past states, then it seems that those past states, in some way, they have to exist. So here I see a difference between Jungian and non-Jungian. In the case of eternalism, I really don't see what the explanatory gap would be. I think that in this case, whether the word is Markovian or not, there is no explanatory gap for the eternalist. So most discussions have been on this connection between temporal ontology and non-Markovianity. There is, however, another connection that has to do with non-Markovianity, Markovianity, and causality and counterfactual. So I know that Lewis has a very quick side note on non-Markovianity in counterfactuals. I'm honest, I didn't understand, I don't know what he said, so if anyone here can explain it to me, I would be happy. My understanding is that at least in order to provide a semantic for counterfactual, if the word is non-Markovian, we have some issues to deal with. So my understanding is that in order to fix the antecedent of any counterfactual, we have to fix the history up to the point of the antecedent. So if we fail to fix the history up to that point, as it is the case in the non-Markovian case, then I think providing the semantic for the counterfactual in the non-Markovian case appears to be harder. Now, I'm going to quickly discuss the last part, which has to do with the interpretation of the noise field. I already mentioned this double standard. So in the standard case, people usually discuss the noise field as an imaginary thing, This is under massing, and it's not part of the ontology. Tim once mentioned to me that maybe Philip is the only one who doesn't have this view, but I never found exactly where he advocates for this. But in the case of the standard white noise model, which are the standard models, usually the idea is that the ontology is given by either the wave function or the mass density. In the case of CSL, the wave function ontology is quite hard to come by. So usually it's mass density. And there is no mention about the noise field, if not as a part of the dynamics, not a part of the ontology. However, in the case of the non-white CSL, we saw that they have they can be seen as a real physical field with different values at different points in space and time. So it's much harder to think of that as a field. It seems that what's natural is that we should interpret this as representing some physical field, which nature is yet to be exactly known, or maybe it will never be known. But it seems to be representing a physical field and not just a field. However, I call this a double standard interpretation because, of course, if you look at the equation, the kind of interaction between the noise, be that white or color, and the mass density is exactly the same kind of interaction. So I think that this teaches us that even in the case of CSL, we should look at the wave, at the white, at the noise field as something real, as possibly part of the ontology, not just of the dynamics, as it is described by the wave function as interacting, and it is described by the wave function as interacting, being coupled with the mass density. So what the wave function does in those models is to couple the wave function, the noise field, and the mass density field. So this is kind of I mean, at least to my knowledge, a new way to look at the noise field as part of the ontology. And of course, it's weird to think that the noise field is part of the ontology or to even understand what this means. But in the end, like similar arguments that are made in order to argue that the ontology of quantum mechanics just is the wave function can be made in this very same context. I think there's some arguments that people make in order to argue that the wave function is the entity that is described by quantum mechanics in the kind of indispensability type of argument, that can be made similarly in this case, for the reasons I mentioned. Okay, that was the end. I'm going to conclude. So as I said, the jury, at least in the case of spontaneous collapse model, the jury is still out with respect to whether the world we live in is Markovian or it's not. So at least the first assumption in Builes and Impagnatiello's paper is not correct. There is a debate about this as we very roughly saw as implications even on the experimental side, and physicists are working on this model. I am not saying that these models should be taken more seriously than their white collar counterpart. I'm just saying that if we are kind of if we have a naturalistic perspective on those models, if we take seriously spontaneous collapse models in general, I think that the non-Markovian models should also be taken seriously because there are many reasons why they should be taken seriously. And of course, if we do take them seriously, then there's going to be some implications having to do with non-Markovianity, though, as I said, I'm quite skeptical that the arguments for non-Markovianity and ontology, apart from some temporal go through. But at least I think it teaches us some important lessons about how to look at the ontology with respect to the noise field. Thank you for being so patient. I'm done.
Other questions, so I will take questions from students first.
Thank you for the talk. So one question is that your theory, the theory seems to be non-local. Yes. So this doesn't seem to be compatible with relativity.
So there is a huge debate about how to make this compatible, about how to extend these models, all these models, in a relativistic case. So there has been attempts both in the case of the CSL models of those models. There is no, not to my knowledge at least, there is no debate on how to make extensions of the non-white color case, but at least in those models there is a debate. There is, I mean, there's people who are trying to make those compatible. Like, yeah.
There is no non-local term, right? There is simply X components. The other term there's like X components.
Yeah, in the non-Markovian case, yeah. But the incompatibility with relativity also happens in this case because well, in general, because in every interpretation of quantum mechanics, whatever the process of collapse is, seems to be instantaneous, or I mean, can be described as instantaneous. Is instantaneous. I was scared to say it. Is instantaneous. But in the case of CSL, what they do is to make the collapse process not instantaneous, but happening. I'm oversimplifying, but happening on a future light cone, for instance. So there's, well, this is one option. But in general, this is as non-local. Well, this is not as non-local. It's non-local in a different way than the other ones, obviously, but it's as problematic to make compatible with relativity as the other one.
That one seems even more problematic, right? So extra correlation.
Well, honestly, I haven't thought about that. I am not sure. I mean, like, so long as, but again, I don't know of people who have worked on this because these are models that even making sense of them in a non-relativistic case is hard. So I'm not sure if they tried. But if you're interested in this topic, Bassi and Girardi have a 150-page long paper introducing everything about those models, and they don't mention any. They mention the non-Markovian case. They obviously mention models that are ways to make the models compatible with relativity, but they never talk about the two things together. Girardi speaks about incompatibility with relativity as a possible motivation to develop those models, even. But again,
because it seems like if you remove the Markovian, non-Markovianity space and have it moving time, then you won't have that text.
I don't think you can do that. You would still have non-locality. So you still have non-locality in time. Sorry, in space in the standard model.
Yeah, sure. I agree with that, but I'm saying the extra problem with g of x minus y. You won't have that term if you remove non-Markovianity.
So you would not have this problem here with GF.
Yeah, I can just remove the spatial dependence equation.
Then what would happen? Sorry.
Then you won't have that extra problem of non-locality.
In time?
No, in space.
Well, but you already have non-locality space.
No, I'm saying if you...
Independently of GF.
Yeah, I agree with that. But I'm saying this is giving an additional problem which can reduce, right? You don't have to...
Okay, maybe I don't get why. I mean, for me, it seems that the other problem is still as big as to require a solution that I don't see how having bigger. I mean, it seems to me that if once, okay, put it this way, maybe I don't get your point, so sorry. But if I got your point, I got your point in the sense that I would have to first see how the compatibility with relativity have been made in the other case in order to see whether this creates a further problem. Maybe it doesn't. I mean, my feeling is that I don't know why. Maybe it doesn't. You know, I don't see a technical reason for thinking that this would create a further problem, so I would have to remove the GX. Sorry, maybe I don't know first, and we can talk about that later. But thank you.
So this slide where you have the expected value, you integrate over both space and time.
Yeah.
You can also demand, I guess, both of them separate.
Why would it change? Sorry?
If you demand two separate space.
Yeah. On the direct delta function.
On your expected value.
Yeah.
So that was, I assume that's both.
Yeah, yeah. And why do you think?
I'm just curious, what if you know what would happen if you applied both? And you just averaging of the space, zero, just averaging.
Would be the same, right? Why do you think it would be different?
I mean, it is obviously, well, it's in the.
No, I mean, you seem to have something in mind, but I don't know why. So I think two of those, one for space and one for time, would make averaging over zero, both of them averaging over zero, should make a difference.
I'm just curious.
No, I don't think so, but maybe, no, they shouldn't make a difference. No. It would be the same, right? I don't have a better reply than this, I'm sorry. Yeah, go on, man.
Especially if it's zero, just a different number of cases.
If you separate them and you erase, in one case you erase the space. Actually, maybe I'm thinking that, so that it might be that the confusion comes from the fact that in the previous slide, I tried to introduce this only as a time-only case. This actually created problems to me also when I tried to publish the paper. But my idea was to first start from the very, very simple case and add the spatial function so that if we go to CSL, we see that we have both spatial and temporal. And then, of course, I come back to the spatial and temporal. Now you're saying, okay, let me separate this in a spatial and a temporal component. Would it make a difference? And my answer is, I don't think so. But if you think it would make a difference, do you have an idea of what it would change? What would it change?
You're asking whether height and separable and the function.
No, wait, I'm just because you never define what the expected value is. Well, it's obviously, you think it's a distribution of space time, so you think, you could also average. That's what it's
And my impression is that nothing would change, but maybe it would. Most likely wouldn't. I mean, it's just adding those just writing them together. I don't know. I don't have further thoughts. I'm sorry, but thank you. Yeah.
Okay, so I have two curiosities. So one is about the difficulty with others, hybrids. Like it seems to me that it's a different problem than just the collapse with consciousness.
Yeah.
Brain space, so I understand how problematic it is. And then the second curiosity is with the.
Do you mind, Margarita, if I reply so I don't forget? Sorry. Yes, what you're saying, I think it's right, and it's also the reason why, I mean, people are not crazy that we have to reject these models. I mean, of course, though, I want to mention that even though it's still a physical process, it doesn't have to do, it's not obscure as the measurement in the primitive sense of standard quantum mechanics is, but still it seems to kind of clash with this idea that, stuff are happening there before we kind of, so my idea is that intuitively, my idea is that in the latent image formation, like something is happening there, and there is image formation, and then when I go there and look, I look at something that already has been formed already. Is that an argument? If that's not the case, is it an objection to standard GRW rate collapse? I don't think so. Or if it is, I still have to see what the argument would be. It's not an objection, but it's at least intuitively, I don't know, unpleasant.
So the brain state.
Yeah, in that case, we have enough particles to produce the collapse in the standard case. While without them, it's enough, it does it by itself in a way. What was the other question?
I was wondering if it could be the closeness station.
what you're saying is the reason why it's a problem is because we fail to.
Evaluate on projects.
Okay, yeah, closeness is a way. I mean, I'm not saying that it's the only way, but of course, if closeness to other words is what gives us the antecedent, then this is a way to really describe. I was trying to be as general as possible. I think you're right. I would have to think more, but I think you're right. I wanted to be as general as possible so as to avoid closeness or proximity or whatever. I haven't thought too long about this. So if it looks to you, because this paper was published already months ago, but only the first part, basically. And then I thought for this occasion, I wanted to do some other stuff. But I mean, I spent a couple of weeks, so it could be. My impression is that this is the case. But if you guys have completely different intuitions, please, because that it's going to be you and not the referee to point them out to me. My understanding is that there's going to be a problem. I'm not saying that it's impossible. I'm saying that you will have to say something. And Lewis does say something, but I didn't understand what. So maybe you know what Lewis says, you understand what Lewis says. Maybe you know your counterfactual. My understanding is that if you have a non-Markovian, if the best system is non-Markovian, then once you fix the antecedent of a counterfactual, how do you fix the antecedent if by fixing the antecedent you're fixing the history up to the point right before? It would be like so changes in the state of described by the antecedents would be ubiquitous, not miraculous. Would be basically ubiquitous because the past state is still not fixed. That's my intuition, but it may be wrong. Thank you.
Would you say that a philosopher defining growing block you would be favored by Non-Markovianity or not?
So favored, so long as well, I think for growing block is the idea that everything up to now exists, the future doesn't. So the past exists, the future doesn't, the present does. So I think everything I tried to articulate about presentism as the same. So everything I could say about growing block is the same as what I said about presentism. So I cannot depend. So if you're non-Markovian, the past exists. Okay, so at least you have that. But I think. Oh no, maybe I don't know. Maybe it's different. Maybe it's different. What do you think? Because it does. Well, you have the past at least.
Yeah. It could be.
Well, I think for them the growing block is as problematic as eternalism in the case of Markovian theories. But in the case of non-Markovianity, I think having the past. Would the past change? I don't know, man. I have to think about it. I haven't thought. I thought like my brain was already challenged with the present scenario, which I don't really. So yeah, but thank you. I have to think more.
And the second question is just whether you think that there might be problem for a special relativity system. So, yeah.
Extension.
Yeah.
Again, my understanding is that I don't know. No idea. My two things I think I understood is that the relativistic extensions are already hard in the standard case, but my impression is that depending on how you attempt to make the spontaneous collapse model relativistic invariant would have an impact. So depending on how you do it, there is not just one way, would have some impact on how you would eventually do it in the non-Markovian case. But this is not like, the second thing I can say is that of which I'm almost certain, is that I'm not aware of anyone who discussed these two very complicated and hard topics together. So people have tried to do them, apart from Girardi, as I mentioned earlier, who actually mentions no relativity as a motivation. Apart from that, but it doesn't, apart from saying that it's a possible, plausible motivation in a very vague and non-formal way, it doesn't add anything. It doesn't say, okay, this would be a possible way to implement the equation, or it doesn't say anything. And then in a completely different sections, he completely different few pages later discusses the relativistic extensions, and he cites Murka, Bellingham, the usual thing. So obviously there is a connection. I have no idea what it is, and so far, from what I know of this discussion, it's already quite hard to kind of make sense of the two things separately. So maybe in a way it's a new venue for research, but don't know much.
Just think that, I just believe this says anything about does it also say the same thing about shrinking? The way you present as non-Markovian, it seems like a
Yeah.
distribution.
That's what I wanted to say. But okay, so that's what I wanted to say, but then I stopped. Okay, what you say is that for what I said about non-Markovianity and about colored noise, everything I said is it's irrelevant whether you look at the past or the future. So if that's the case, then the growing block case would have to be symmetric to the shrinking block case, which is where you only have the future, but you don't have the past anymore, and you do have the present. So again, my head tends to explode when I think about temporal ontology. It's not something. There's people here with temporal ontology. I really don't. But it's an interesting case to think about, because for what I said, again, the case is both past and future. But I think the problem when we look at the standard problem with temporal ontology, as it was presented, for instance, by Adlam, was that, look, if you have non-Markovianity, the future doesn't really matter. What matters is that the past is influencing. Okay, and if the past is influencing, how could it be that it doesn't exist? Because what is the dynamically relevant up to the state now is the past. Your T to now. From every time in the past to now, obviously not the future. So if you look at the introduction of the non-white noise, then yes, it's irrelevant. But of course, if you look at the equation, it's the past that is dynamically relevant. Luckily, I would say. But yeah. But
Okay. Yeah, just I follow up on the question of relativity. The notion of Markovianity that you present and seem to propose that it makes sense about past. So is there a way to recover a similar notion in relativity? A notion similar to Markovianity, which does not presuppose.
Well, I would not say that with non-Markovianity it makes no sense to talk about the past.
No, just the notion of Markovianity.
Yeah.
Seems to presuppose that it makes sense to talk about
the
the
notion of
Markovianity future. Sense.
Yes, but also talking about the Markovianity case now.
Or no Markovianity.
Yes, then I agree. Okay, I thought you wanted to make a distinction between the two cases. Yes, in both cases, it does make sense to talk about that.
That's why.
Right. So the question is, when you move to relativity, where it doesn't make much sense to talk about past, present, and future, can you recover a notion of relativistic Markovianity?
It's not that it doesn't make sense. I mean, it makes sense with respect to a certain hyperplane.
Right. Yes. Yeah. So it's not an absolute.
Yeah, it's not absolute, but you can talk about Markovianity in
a frame.
Yeah, I mean, it's not problematic. Well, what you may not be able to do is to think of past, present, and future as absolute. But this is not necessarily a consequence of Markovianity, that they are absolute. the consequence is that if I look at a certain system, I can talk about past, present, and future. And in the Markovian case, whatever happened in the past for that system is irrelevant. If it was, I mean, so yeah, that's my.
So in relativity, the notion of the universe being Markovian is relative.
Yes. Quite safe to say yes. But maybe someone. I'm not giving very final decisive answer, I understand.
So clearly, so in the matter density ontology, in sort of the Markovian case, you're creating over space. So now you have something which is spread out over, like your fundamental ontology is smeared out in space. So now that you have non-Markovian, is your fundamental ontology also smeared out in time? That sort of what is basically there with your physical ontology is not something that's now being spread out over time.
Interesting, very cool. So, very nice. No, well, so if I am correct that it makes any sense, which is a big if, which makes any sense to look at the ontology of these equations and, for the reasons I mentioned, also the other ones, as describing an interaction between those two. I think that all the temporal non-locality is in the noise field. Relativity aside, because now I'm relativistic now. So in the non-relativistic case, this would still be the very same old dear old mass density in my understanding, and this would be non-local in time. So then when you say the mass density would also be non-local, I don't know what it means, but apart from what it's already non-local in quantum mechanics, that there is not more non-locality in the mass density than there is already. But it's a fun question. I have to think more. But my understanding is if your ontology is just this, okay, as it was the case in the standard models, and this is not part of the ontology, it's just an imaginary tree. It's not representing any physical field. Then in the non-Markovian case, this would act very weirdly, because that's not a trick anymore. It's not just the dynamics. This would act in a very much weirder way than it already did in the other case. But once you look at this as some kind of physical field, which is, I don't know what it's representing, then the mass density, I think, is the same.
There is no time.
Well, yes.
No, it's integrating over time.
Yeah.
Unlike in the non-Markovian.
Yeah, but then
in the Markovian case, there's no integral over time. You're talking about time of it. No, just like whatever is supposed to be the basic ontology, whether if it is M of x or WT x times. If the coupled thing is supposed to be the basic ontology, then but the coupled thing is not. The product is only.
For me, I think it depends what you mean when you say that MT is non-local over time. I mean, what do you mean exactly when you say it's non-local over time, apart from being affected by this non-local in a temporary non-local way? So when you say it's non-local over time, you mean that this has temporally non-local effects on this. Thank you. I was not expecting such an enthusiasm towards this stuff. I'm very happy.
Yeah, question from students. Or more students. Yeah,
I'm just continue.
yeah.
So the M is also a function of
Mhm.
can you write a dynamic equation for like the time function of
In this case,
Yeah, is it, or in both cases, is there anything reasonably listed?
sorry,
Then
then
you just write, if then we, can you write the equation for the type evolution?
that's the equation for the time evolution of M.
Well, that's for psi.
Well, the evolution of, yes, but the evolution of psi is given by, so the interaction between M and, I don't know what you're asking. So you're asking how this evolves irrespectively of psi?
Well, I'm trying to get to, if you want just M as the fundamental ontology, what's the role of psi?
Again, depends on what you think. Okay, one thing would be that you need both psi and M to give you the ontology. Another option is that the ontology would be given by these two, and psi is what tells you how they interact. But then you're asking something more, which I'm not sure I understand. Maybe Tim does, because he has a finger.
I'm sorry. Yeah, this is just related to this question. So what you've written there, it looks kind of funny, right? Because you've got that integral, d3x, some function of x, some other function of x, dt with no function of t. I mean, t is not listed as a variable for anything under that interval where you're then integrating them with that. I don't understand what's being integrated. Should there, are there, I mean, is there a suppressed e variable somewhere?
Maybe I forgot to mention something, but don't understand what. There should be a t somewhere here.
I mean, you've got a subscript key. It's not put in as a
Oh, I see. Yeah.
even that's in W. You're saying somehow there's these things. Yeah,
I see.
no, literally no letter T.
Yeah, no, yeah. That I now understand a lot of first. It's fine. I see what you mean. Thank you. So yeah, I mean, this is still the form of this equation. I have to see what I messed up. So thank you.
You know, I mean, where you've got an yes, okay, you've got an S.
Yeah, I mean, here, yeah, I don't have the S.
There you've got a DT and it isn't.
Yeah, you're right.
Oh, with white noise, it's very common to have the t dependence.
I think that's why I just started with, yeah, I messed up for this, exactly for this reason. Thank you. Yeah. Yeah, I messed up something.
It's correct, right? The time dependent, there is time dependence. Instead of W of x comma t, we simply write as W.
Yeah, it's t here, right?
And then the other thing is the embodiments actually have limits on your key integral, but here you're seeing you don't have any limits on. So the integral is t from something.
But here I was being here, you mean? Here I was
You
being.
put the limits here.
Yeah.
There are no limits on that. That's the.
No, you should have the limit. You should have the limit here. You only need the limit here. You don't need the limit there.
But so that's an indefinite interval. I'm sorry. It's just not.
No, I think I see the other problem. I'm not sure I see this one. But on the other problem, I should have t here. But then, no.
I just want to look at the domain of inversion.
Well, in this case, it's t to t0.
No, but what for the upper t? Is that an interval over all t?
Yeah.
Negative infinity and positive infinity?
Well, as it was the case in the other one, right?
I don't know exactly.
Yeah, I mean, I didn't mention it in the other one. Yeah, no, it wasn't. I think here it's not important to mention it. It's both infinities. While here I have to mention it because
I guess the question here is that the integral here is from t to t0, and the question is.
Yeah. These are two separate questions, though, right? So it's first, where does t come from here, And the second one is why here I'm integrating and here I'm not.
But the interval would be the same.
It wouldn't be the same. But that's to reply at least to the second question. But I have to look back at this equation and see what the problem is. But I agree. I think lucky enough, I still have time. So thank you.
Yeah, is that kind of conceptual for a second?
Yes.
Step when we go on with it. You said things like if it's Markovian, the past is ineffective or
Doesn't have a direct influence.
so I'm trying to understand what's the nature of that. I mean, okay, in a Markovian system, you define it just in terms of screening law. The idea is present. Okay, the present, as far as predicting the future, you do it in the present state, and derive some probabilities. They're unchanged if I get an addition condition on things with the past. Sounds like you're saying, oh, that makes the past inert or non-existent or unimportant. But that screening off works perfectly well in all kinds of ways. Give me some task types. No,
Not in a non-Markovian case.
no, in a Markovian.
Yeah, in a Markovian.
I'm not sure, am I supposed to imply that then the present doesn't exist or has no causal powers?
No. I
I mean, I'm just trying to understand that, what is the nature of this inference to blah, 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 therefore the present is, the past is, doesn't cause anything or doesn't. I'm just not quite understanding.
Okay, so if I said that the past doesn't exist when I'm talking about Markovian case, I hope I didn't say that because
I don't know.
No, what I said was that there is no influence from the past to the present more than what the past has already influenced. Sorry, there is no more influence from the past to the future than what than the influence that the past already made to the present.
Oh, okay, all right.
So whatever present, if you have a present now, whatever state you have now in the Markovian case, what happens in the future only depends on what you have here. So no matter how you got there, that's the resonates now.
Right, so yeah, so it has no more
Than what has already
not that it
had.
doesn't have it.
But yeah, if you say then one has then the influence that already had, I think is a good close one. Also because it excludes the non-Markovian. Because in the non-Markovian case, it could have more influence in the future than the one that already had. You already had some influence because we got to that present state because of the past, but it may have more influence than the one already had. Does that make a little bit more sense?
Yeah.
Thank you.
Yes, I have a question. So it's about the physicality of the noise.
Oh yeah.
So like in the first case, you said it's like a organization, like in the second case, you said, okay, can you go to the other slide? So you said it's interpreted ontologically as like
It could be interpreted
yeah,
that.
could be okay. And then you also have a slide where you have like reasons to say it's like I think
Yeah.
yeah. Like one reason is that the non-white CSL changes of experimental testable impacts. That's one reason.
I think that's the main one for this.
Okay, but then I guess like I suppose also in the other case, if you change the white noise field, there must be some testable difference.
What do you mean by changing the way? So that white noise field is, cannot be changed. It's just
Yeah,
white
but
noise.
if you plug in a different function. Yes. What do you mean by the fact that changes in the field?
So,
In this case, but not in the other.
So in this case, you can have different noise fields, so you can be colored in many ways, but you can be white only in one way. So that's the first difference. And the second difference is that in the non-Markovian case, depending on the color it noise has, the noise will interact in a different way with different frequencies. So if you change, so this would mean a fortiori that depending on, for instance, the mass of certain what mass a certain particle has, what type of particle it is, and so what mass it has, it would be affected differently by the noise. While in the white case, the influence would be the same. Does that reply to your question?
So is that just like an hypo?
A what?
Like does it have any function here?
It's it's not a function in the strict sense because it's not measured. If you take the white noise at any point, you cannot measure it. Because you don't know anything about the future. So there's a sense in which it's not technically a function. While in the color case, it is, and it could be different.
Yeah, so that's not really a double standard interpretation, right? In one case, that's a good reason why it's potentially physical.
I think the double standard thing is just based on realizing that sorry, in both cases the kind of interaction is between this field and the mass density. Now, why would it make a difference what this field is? And then you say, well, the difference could be that in one case this is a function, in the other case it's not. But the kind of interaction is still the same. Seems to be a physical interaction between this noise field, whatever the color is, and the mass density. Modulo all the issues that we discussed earlier. So I think the double standard still is kind of again, it's not an objection, it's kind of a motivation for exploring this view. Because no one would say in the non-white case that this is not representing something. Then, of course, people would disagree on what it's representing. Most people would say could be representing something we still have to understand. They're not, thinking that it's I don't know what noise field is, but in the other case, everyone says it's a noise trick. It's just a trick.
Yes.
Maybe some question. One can we anything about the nature of time on this Markovian concept, but not on any
Okay, so it's a good point. I think what they are doing is, I think it's a very good question. So, and the reason why it may not have been clear is because I didn't explain something. So for these people, we can kind of extract the meaning of Markovian from the standard meaning that usually we associate with stochastic processes, and kind of use it to look at wars or entire histories of certain universe. And so it's not just in the standard sense as referring to a stochastic process, but it's more generally referring to a property that laws of nature may have. So it's not just a certain process. This is not referring to a certain process as in the standard case, but to more generally the laws and how events unfold, all events unfold over time. So in this sense, a fortiori, if it's all events unfold over time, it also refers to any kind of process that happens in that world. It was a good point. Thank you.
Okay. We are seeing.
Finger?
Yeah. Complicated ones. I never studied any of these protocols. This double standard thing. So you say there's only one way for the spectrum to be white. If you say it's white, it's white. There are different ways for it to be colored, obviously. Now you have two possibilities. One is you say, look, it's colored, and it's only colored one way.
That's
Colored
the
like
point.
this.
Brown.
Or you could say it's colored, and furthermore, the color changes. The color itself is dynamic. The color itself is not static over time. Now, I guess I can see why someone, if you go to the second group and you say the actual color distribution is changing over time, then for reasons that come up in other discussions of laws, someone might say that doesn't sound like a law. Laws themselves do not evolve. Anything that evolves, you need a law about how it evolves. But the laws themselves don't evolve. So it kind of fixed non-white theory seems to me to be on the same standing as the white theory. I mean, the reason why people might say, look, the thing, there doesn't actually have to be a field there. It's just a way of specifying a certain stochastic process. And saying it's white fixes that stochastic process. Saying it's just, fire engine red, or I don't know how you characterize the colors. And it's always fire engine red. That would also fix the stochastic process.
Yeah, it would.
Of course, if you said, well, it's not, it changes. Sometimes it's white, sometimes it's red.
That's not what I want.
Then I can see what's going to say now it's more like a field. Right? And actually now I need a whole law about the changes in the colors. But the way you have it written, it's just like if it's white, then you can do this color, you can do something else. I'm just trying to understand why.
No, I get that. So no, I didn't mean to say that the reason why we should look at the non-white field as a physical field has to do with the fact that the color itself, the ways in which the frequencies that are affected change does it over time. I didn't mean to say that. I mean that the reason why we may look at this at a field has first to do with the fact that usually when we say a physical field, the physical field has some temporal correlation of some kind. And so what we say is that, okay, this is representing something, like in the case of Brownian motion, we think that it's representing something, which is the only color that is named because of the guy, or because of the dog, because it's pink, actually. Anyway, so you know that there's something there. You describe it stochastically in this way, but you know that there is more. So what people think is something similar. What I gather people think is something similar. If it's non-white, then it's gonna be representing something, even if the color doesn't change, because it doesn't in this case. So even if the color doesn't change, and by the way, the color doesn't change, meaning the color doesn't change over time. We have a color that is not white, but it's the same color, like in the Brownian case. Not white, but it's always brown. It doesn't, in the Brownian motion, the color of the noise keeps being pink all the time, right? So here, I mean, you can describe the field using different colors, but then when you pick this color, maybe there is also some very exoteric view where it does change over time, but that's not what I meant to say. Yeah. And if it does, then I fully agree with you, I would not like for the reasons that you mentioned.
Okay, so the question is why, suppose it's just fixed.
Yeah.
Why treat white and color in different ways? Is that the double standard? Because I can't see why. I mean, they're just different stochastic.
Exactly. There are different stochastic processes, but then in the white case, people don't even think that it's represented. They just say, well, that's a useful mathematical device to do exactly what this. Just change the color, and people say, it's representing something.
Okay.
But what what I'm saying is, no matter what you think that the WT is representing, just keep one answer in both cases. Okay, that's the negative part of mine. Then the positive part is, look, we haven't thought about that. Just let's consider that since if you look at the equation, these are coupled, obviously. Why not thinking that this is a field of some kind, even in the white case? But in the non-white case, people are already saying. I think we agree on this, which is good. Always good to agree with you.
Let's continue the conversation at the top.
Or not. Thank you.